Voice agents are in their Renaissance era. We're moving away from clunky interactions with Alexa and Siri towards more natural real-time conversations.
Could you order my usual margarita from Luigi's? Delivery here.
Sure thing. Your usual medium margarita with thin crust. On your office address?
Yeah.
But what exactly is hiding behind these new voice agents? How are they taking advantage of the LLM revolution? And also, why are they so late? At this point, even GPT-4 is about 3 years old. To answer these questions, we'll look at Voxtral, an open-weights family of real-time voice models from Mistral, who are also sponsoring this video. In an increasingly opaque industry, their detailed technical reports are the reason why I can keep making educational content. So let's see what's hiding behind this trench coat.
What's the meaning of life?
Some would say 42.
When building voice agents with a speech-to-speech interface, there are actually two schools of thought. One is modular, nesting an LLM between two other powerful models. This is the more practical approach, embraced among others by Voxtral, and will be the focus for this video. The alternative is end-to-end models, which treat speech as a first-class citizen and remove the text bottleneck. Thinking machines is one of the most visible proponents for this approach, and we'll talk about it in the next video. A modular voice agent is really 3 modules chained together. A speech-to-text model transcribes the audio into text. It's also commonly known as an automated speech recognition model, or ASR. Its output is fed into a standard LLM, which does the heavy reasoning. The response finally goes through a text-to-speech, or TTS model, which maps it back to an audio output. These 3 components are trained separately and only communicate through text. The most obvious benefit of this loose decoupling is that you can mix and match. For each stage, you're free to pick the single best model for your use case. Say you're running customer support for a European bank that serves a dozen countries. Then you'll prioritize an ASR model that does well on European languages and are probably willing to compromise on Chinese quality. Then you'll take the LLM and fine-tune it on the bank's playbooks. Also, for the text-to-speech model, you might want to prioritize latency as opposed to emotional nuance or rich acoustics. On the one hand, having text as an intermediate representation is convenient for debugging and provides an auditable paper trail in regulated settings. But on the other hand, it throws away all the nonverbal information in the audio input, like frustration, sarcasm, or hesitation. And chaining 3 models means latency accumulates at every stage. There's just no free lunch. The Voxtral voice models from Mistral can be plugged in as components of a modular pipeline. We'll look at 2 of them: Voxtral Realtime for speech-to-text and Voxtral TTS for text-to-speech. In isolation, they're both streaming models, meaning they start producing output almost immediately rather than waiting for the full input. For speech-to-text, that means Voxtral Realtime starts transcribing almost as soon as you're talking. It's supercalifragilisticexpialidocious, even though the sound of it is something quite atrocious. Compare this to an offline transcription model like OpenAI's Whisper. It's supercalifragilisticexpialidocious, even though the sound of it is something quite atrocious. It waits for the entire voice recording to be ready before starting to process it. And the entire transcription shows up all at once. So what's the difference then? What does it take for an audio model to work in real time? But perhaps the better question to start with is, what exactly qualifies as real time? What's an acceptable delay between speech and its corresponding transcription? Is it under a second, 3 seconds, 30 seconds? The truth is, there's no supreme authority that draws the line, but most of us would probably place it somewhere around 3 seconds. OpenAI's Whisper sits at the very end of the spectrum with a context window of 30 seconds. It's an open-source speech-to-text model trained on 680,000 hours of weekly supervised audio. That means imperfect transcriptions curated from the internet or generated automatically without manual curation. Even though it was released back in 2022, Whisper remains the most widely deployed offline transcription model in the world and is a strong overall baseline. Voxtral Realtime allows a user-tunable delay between 80 milliseconds and 2.4 seconds, and we'll see shortly how they implemented this adjustability. Obviously, we're trading latency for quality. Somewhere after the 480 millisecond mark, Voxtral's word error rate becomes on par with Whisper, despite not having access to a full 30-second window of audio. So what exactly enables this performance? Well, let's work it out backwards from the output. Here, I've modified Voxtral's official Hugging Face space to surface the raw output tokens. If you look at their timestamps, you'll notice that a new output token is emitted every 80 milliseconds. This is the cadence of a streaming model. You'll also notice two special tokens: padding, which communicates "I'm still listening" or "I'm still processing," and the word boundary, placed right before a stream of actual text tokens. These are all artifacts of a recent modeling framework called Delayed Streams Modeling, or DSM. It comes from a Paris-based company called Qt AI. We'll hear more from them in the next video. DSM introduced this idea of a heartbeat. Both audio and text streams advance at a regular cadence, say 80 milliseconds. So on each heartbeat, a speech-to-text model processes an audio frame of 80 milliseconds and also outputs a text token corresponding to a previous audio frame. The text stream is therefore delayed by a few heartbeats, since obviously you can only transcribe things that have already been said. That's why Voxtral's output starts with a bunch of padding tokens. Say we set the desired delay to 160 milliseconds. Then the first two pads enforce this delay, and the rest are just accounting for silence, since I didn't start speaking immediately after pressing record. If you're a machine learning practitioner, your first question might be, how do you even train such a thing in the first place? Well, the first requirement is training data that aligns audio and text at a word level, so that the model learns precisely what to say and when. You'll need something like this JSON file where every word comes with its own start and end timestamps. And what about the configurable delay between audio and text? Say that the model supports delays between 80 to 2400 milliseconds, that is, from 1 to 30 heartbeats. To support this entire range, the DSM framework picks a random delay for each training batch, offsets the text stream by that amount, and fills the gap with padding tokens. Delayed streams modeling is a huge enabler for streaming models, but if we're being realistic, it's not rocket science. It's quite an obvious algorithm. So why did it take so long for it to be published in 2024? Well, the truth is, streaming models have existed for a long time, but they used to be implemented with recurrent neural networks, which are a very natural architectural fit. The original transformer, however, was less so. So the true value of DSM is to bring streaming to the transformer in a way that enables pre-trained LLMs to bootstrap speech models. Contrary to common belief, the original transformer, as published in 2017, was intended for offline machine translation, mapping a piece of text from a source to a target language. The language modeling revolution actually happened later. I covered this in one of my previous videos. Now, speech-to-text is inherently a translation problem, not between languages, but between modalities. That's why offline speech-to-text models like OpenAI's Whisper were based on the original transformer architecture. At the time, it had two core components: an encoder to process the source sentence, and a decoder to generate the translation autoregressively. Because the source sentence was assumed to be available in full, the encoder used bidirectional attention, where each token embedding depended both on its left and right context. This is what limited Whisper's real-time capabilities. It needed a full 30-second context window before it could start transcribing. Of course, people have hacked around this limitation. Take Whisper streaming, for example. It wraps the existing offline model with an API that mimics real-time behavior by keeping an internal audio buffer capped at 30 seconds. Once the audio buffer is filled, whisper streaming makes its first call to whisper. When a new chunk arrives, it displaces the oldest one in the queue and triggers yet another call to whisper. This did simulate real-time behavior with just a few hundred milliseconds delay and only a small hit in accuracy. But it was ultimately still a wasteful hack, since the same audio chunks were transcribed repeatedly. Plus, there was a mismatch between training and inference. Whisper was trained on full sentences, but whisper streaming was calling it with incomplete sentences and even incomplete words. In contrast, modern speech-to-text models like Voxtral Realtime treat streaming as a first-class citizen. The first step is to completely rethink the encoder, toss away the bidirectional attention, and replace it with causal attention, so that each audio chunk only depends on previous ones. In theory, this should be enough to enable streaming behavior. But as I mentioned earlier, the biggest value proposition of DSM is to enable pre-existing pre-trained LLMs to bootstrap speech models. Since most LLMs today are shaped as a transformer decoder, the decoder is a natural place to plug them in. In particular, Voxtral Realtime leverages Mistral 3B. This is a completely different LLM from the one that sits in the middle of a modular voice assistant. It's an internal component of the speech-to-text model, and it gets fine-tuned for this task. Given the presence of this LLM, we also need to reconsider how the encoder connects to the decoder, since this cross-attention doesn't come with the LLM. Instead, we'll move the audio encoder downstream. Once contextualized, audio embeddings are directly added to the corresponding token embeddings. This way, audio and text are processed at the same pace by design. From the point of view of the LLM, there's a single input token for each heartbeat. It's just that under the wraps, that input token is the sum of audio and text embeddings. And this is the architecture of real-time speech-to-text models that follow the DSM framework. This is what Voxtral Realtime builds upon, making additional adjustments that ensure training stability. One of their innovations is a technique called adaptive RMS norm. It's a new way of communicating to the model the desired delay selected by the user at inference time. If you're familiar with such architectural details, you'll immediately think of adaptive layer norm, a similar trick used by the diffusion transformer to inject the diffusion step, which I've covered in this other video. So once audio is transcribed by a speech-to-text model like Voxtral Realtime, it can then be fed into an LLM, again, different from the internal one. This LLM reasons over the user query, maybe even calls some tools in the process, and outputs a text response. Then a text-to-speech model turns it into audio, which brings us to Voxtral TTS. Just like its sibling, Voxtral TTS is in isolation a real-time model that produces audio autoregressively.
It's supercalifragilisticexpialidocious, even though the sound of it is something quite atrocious.
Its time to first audio is around 70 milliseconds on an H200 GPU. So how does audio generation work? Voxtral TTS accepts two inputs, a piece of text and an audio recording with a voice reference, somewhere between 3 and 30 seconds, that will guide what the output sounds like. It's what we call voice cloning. Under the hood, it's an autoregressive LLM that additionally takes in its previously generated audio tokens and predicts the next one. But what exactly is an audio token? How can it be fed into an LLM, and how does it compare to a text token? To understand that, we need to start with the basics.
What's the meaning of life?
When we digitize sound, the microphone takes discrete measurements or samples of the wave's amplitude at regular intervals in time. The sample rate, that is the number of samples per second, is measured in hertz. High-quality speech requires at least 24 kilohertz. In 2016, DeepMind's WaveNet was the first neural network that attempted to model a raw waveform directly. Given that this was about a decade ago, its outputs were remarkably natural sounding. Here's one example.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
However, WaveNet was notoriously slow since it had to generate 24,000 samples per second sequentially. For real time, a new sample would have to be generated every 42 microseconds. NVIDIA actually pulled it off with a V100 GPU by fusing the whole WaveNet model into a single kernel and caching the weights in the registers. But that's already scraping the bottom of the barrel in terms of optimization headroom, and we know that model sizes scale a lot faster than hardware capabilities. A more pragmatic approach came 5 years later with models like SoundStream from Google and Codec from Meta. Instead of predicting individual samples, they worked with frames. These were sequences of 240 samples or 10 milliseconds of audio. And this strategy survived until today. Now, we've already encountered audio frames in the context of speech-to-text, where the audio stream was split into fixed-size windows, and each window was converted into a continuous embedding. In contrast, in the TTS world, audio frames are treated as indivisible units, much like text tokens. Predicting a single audio token ID instead of all the values in the frame makes the problem more tractable. For instance, Voxtral TTS uses 80 millisecond audio frames. This brings the real-time requirement down from 24,000 to only 12.5 sequential predictions per second. But this brings an interesting challenge: audio tokenization. We know, of course, that text tokenization relies on a vocabulary that maps integer indices to character strings. What exactly is the audio equivalent of character strings here? In theory, we could simply store raw sequences of amplitudes, but their space is combinatorially huge. Plus, raw amplitude captures the wrong level of abstraction. The same word spoken at a slightly different volume or speed becomes an almost entirely different vector.
What's the meaning of life?
What's the meaning of life?
What's the meaning of life?
Instead, audio tokens are compressed in a latent space where vector similarity is meaningful. Because these entries are called codes, the vocabulary is actually called a codebook. So how is this codebook built? Well, first of all, we need a way to induce this latent space. The standard machine learning solution across all modalities is an encoder-decoder model. It takes in the raw signal, which is highly dimensional, passes it through a low-dimensional bottleneck, and then reconstructs it. In the audio world, this model is known as a codec, which comes from coder-decoder. It plays a similar role to the VAE model used for image generation, though it's trained with a very different loss. Modern codecs apply vector quantization, or VQ, right after the bottleneck. They define a codebook of the desired size. In Voxtral's case, a bit over 8,000 codes with 256 dimensions each. The compressed latent is then snapped to the nearest entry in the codebook. This gives us a code, which is a vector of 256 values, as well as an integer index. The code is then passed on to the decoder to complete the forward pass. This way, the codebook entries are learned together with a codec. The integer index will only serve later when training the actual text-to-speech model. Now, this is a valid tokenization scheme, but arguably, audio is too rich of a signal to be captured in around 8,000 tokens. One option would be to simply increase the codebook size. After all, a text vocabulary can go up to 250,000 tokens. However, empirically, large audio codebooks lead to a phenomenon called codebook collapse, where most entries remain unused. There are two effective alternatives to vector quantization. One is residual vector quantization, or RVQ. After the first level of quantization, there's inevitably a small error or residual. That's the difference between the original embedding and the code we picked. Instead of ignoring it, RVQ quantizes the residual with a second codebook, then a third, and so on. This way, each layer of quantization captures finer and finer detail. The second alternative to vector quantization makes a different trade-off. Finite scalar quantization, or FSQ, treats vector dimensions independently. For any particular feature, its range of values is split into n buckets, say 20. For simplicity, let's assume all features fall between -1 and +1. Quantizing an input feature means snapping it to the middle of its bucket. So for instance, minus 0.72 turns into minus 0.75. FSQ is more memory efficient since there's no codebook needed, and you can trivially tweak its precision by increasing the number of buckets. However, it fails to capture correlations between dimensions. Plus, every single feature in the original latent now gets its own integer index. This is different from vector quantization, where the entire input embedding is mapped to a single integer. Since these three types of quantization make different trade-offs, modern audio models mix and match them in various ways without having converged to a standard solution. Let's see how Voxtral tackles this challenge. The quantization strategy used by the Voxtral Codec reflects an older philosophy about speech. The philosophy comes from AudioLM, a Google model from 2022 that decomposes audio into two orthogonal aspects: what is being said and how it's being said. Every audio frame is decomposed into two embeddings. The semantic part captures phonemes or words and their meaning, and the acoustic part reflects aspects like the speaker timbre, prosody, emotion, microphone characteristics, breath sounds, and so on. The Voxtral Codec quantizes the two latents separately, the semantic one with vector quantization and the acoustic one with finite scalar quantization. This choice is quite intuitive. Semantics are tied to words, which are naturally clustered by meaning and can more credibly be organized into a codebook. Intuitively, similar words should map to the same code. Acoustics, on the other hand, are more continuous in nature and require higher precision, which is what FSQ offers. So the codec is an auxiliary model that can take an audio frame as a sequence of amplitudes and turn it into an audio token, which is the basic building block of the actual TTS model. But at this point, there's still a discrepancy between the codec and the TTS model. The codec factorizes tokens into semantic and acoustic parts, but the autoregressive prediction model expects indivisible audio tokens. Here's how this conflict gets resolved. After quantization, each audio frame gets one semantic token ID, which comes from the VQ codebook, and multiple acoustic IDs, because FSQ gives you a separate integer for every dimension. From here, we'll treat audio tokens, or rather audio subtokens, similarly to text tokens. Remember, an LLM contains an embedding table that maps token IDs to internal continuous representations. All we need to do is extend this table with new entries for audio tokens, that is, about 8,000 more for the codebook tokens, and groups of 20 buckets for each acoustic feature. Once semantic and acoustic tokens are looked up in the LLM embedding table, we can collapse their stacks by summing up the embeddings. And from here on, all tokens share the same interface and can therefore flow through a regular LLM. Well, almost regular, because we'll have to change its output dictionary. Swap out the text vocabulary and swap in the semantic codebook. This way, on each iteration, the LLM produces a semantic token ID. The acoustic part, though, needs special treatment. As we discussed earlier, acoustics don't have the same clustered nature. It's a lot harder to discretize and predict them using an inherently discrete LLM. If you've been following my channel, you already know about flow matching, the generative algorithm behind modern image generation. It learns a velocity field that transports noise directly towards the data distribution in a fixed number of steps. The same idea applies to audio. Starting with a noisy vector and refining it 8 times, the output becomes a clean prediction of the acoustic latent. The conditioning signal is the last hidden state of the LLM, which has been shaped by the voice reference from the context window. This is how the speaker's timbre and acoustic character get transferred, because the LLM has been attending to the voice reference all along. By applying FSQ to the flow matching output, we get our stack of acoustic token IDs. In the next autoregressive step, all output token IDs make their way back to the input, and the cycle repeats exactly 12.5 times per second. To produce an actual waveform, the output token IDs are dequantized into real values and passed through the decoder part of the codec. This is quite an involved journey for the clean acoustic latent. Initially, it's a continuous vector, then quantized, immediately dequantized, then expanded into another latent space by the codec decoder. A similar complexity is present in the loss function. The codec loss has 5 separate terms, including distillation from whisper and an adversarial term. And the full Voxtral TTS adds cross-entropy for semantic tokens, flow matching loss on acoustics, and direct preference optimization for both. This goes to show that text-to-speech is a really difficult problem. It's an active field of research that hasn't yet converged to a simple and canonical solution. Today, most voice systems in production take the modular approach because it's customizable and interpretable. Now, the Voxtral speech-to-text and text-to-speech models are real-time in isolation, but the LLM in the middle is a limiting factor for a voice-to-voice system. The text bottleneck drops the audio, and together with it, emotions like sarcasm or frustration that might actually be relevant in addressing the user query. In the next video, we'll look at models that were trained end-to-end with streaming and interactivity in mind. If Voxtral piqued your interest, you can play with both models right now in Mistral Studio. Same place you'll find Mistral's LLMs and tools for building agents and workflows. In the meantime, you can find my full reading list and my Miro board for this video on Patreon. Thanks for watching, and I'll see you next time.